This is Jiwon Kim from Purdue University. In this talk, I'll present Intender, fuzzing intent-based networking with intent state transition guidance. Before entering our research work, let me introduce intent-based networking. In traditional networking, network updates are very complicated. However, according to Cisco survey, 95% of network updates are manually done, which may cause human error. So 2 years ago, Facebook has an outage due to human error. And 2 years ago, in South Korea, there has a nationwide outage due to single error in router configuration. And also this year, there is a mobile network outage in Channel Island, Europe. With IBN controller, you don't have to care about this issue. And network operator simply says that allowing access from marketing team to database via load balancer. And this is the intent, which is an input for intent-based networking. IBN networking receives this intent and translates into network-level intents with more declarative grammars, and compile these intents into network objects like configuration files and network flow rules, and implement these objects into network devices such as switches or load balancers. After then, IBN controller monitors any data from network devices such as network events or telemetry data. Then it is used for verification to decide whether this intent is correctly installed or not, or the details of the traffic. Then in the optimization stage, it delivers a summarized information of the traffic. Then furthermore, IBN controller can recommend a new type of intents, such as allowing without congestion. In summary, IBN controller consists of 6 stages with a large loop. And while stepping each stage, it creates an intent state machine to represent internal state transitions, like requested, compiling, installing. And after the verification, this intent state can go to either installed or failed. If there is a network change, it goes back to the compilation, and intent state also goes back to the compiling. This intent can be deleted. In that case, intent state goes to removed. This intent state machine is the core idea of our research work. IBN evolves from software-defined networking. And since 2008, SDN has been announced in many implementations, including open source projects such as OpenAI Lite and ONOS controller and Paradox. And in ONOS controller, IBN has supported in 2014. After then, IBN has been implemented in many implementations, including open source projects like Open Network Automation Platform, and 2 years ago, Google announced its internal use. Accordingly, the number of vulnerabilities of both domains have increased. As SDN vulnerabilities introduce a new type of vulnerabilities, IBN vulnerabilities also introduce a new type of vulnerabilities and increase more and more. So how can we find vulnerabilities and new bugs? We apply fuzzing here. As you might know well, fuzzing works as follows. Fuzzers gives random input to target program, and it will return 2 results. First, whether the program makes a crash or not. Second, whether this new input traverses a new path of the program, which is called coverage. And this coverage is used for feedback of the fuzzer. AFL is one of well-known fuzzers. So let's run AFL on fuzzing IBN. However, it doesn't work well. To explain this, let me explain each feature of the fuzzing. And let's talk about crash first. To understand crash, we studied 186 ONOS bug reports. And among them, 61% of bugs are semantic bugs. And the others are syntactic bugs, which are obvious to be found with exceptions, logs, or crashes. However, semantic bugs generate inconsistent state of intents, connection failure, making an impact on existing intents, and creating garbage rules. Such semantic bugs often do not cause any program crash, so we need domain-specific detection methods for fuzzing IBN. So we now know that IBN has a lot of semantic bugs, but what about random intent? Are these all intents valid for IBN, which is not? To show that, we put 2 different networks. On the left, there are Alice and Bob. On the right, Carol and David. And we will install 2 identical intents to support connection between Alice and Bob. On the left, this intent will be stored correctly because the intent information is correctly matched with the network. But on the right, it is not because there's no Alice and Bob on the network. In other words, the success of an intent depends on the network, not depending upon IBN controller. So we need topology awareness to generate valid inputs. Now we learned that topology awareness is necessary. Lastly, let's talk about coverage. Code coverage guidance is well used in these days, but there is a limitation in IBN. So I will explain with the corner case while installing or deleting this intent with different key K or K prime. On the case 1, I will install 2 intents first and delete one of the existing intents. On the case 2, I will just switch 2 last operations. The final result of the intent will be intent K prime because intent K is removed on both cases. However, the connection result can be different. In terms of number of operations, IBN controller can be divided into 3 layers: API, intent management, and flow rule management. And on both cases, 2 sets of installation and 1 set of deletion will be called in each layer. Then let's focus on last operation. Case 1 was deletion. It deletes flow rules finally, which makes connection failure. However, in case 2, it was installation, so flow rules are added, which makes connection successfully. So final results are different, even though the number of operations are same. In other words, code coverage which reads only the number of operations cannot differentiate 2 cases. Instead, the order of operations, such as intent state changes based on our intent state machine, does matter. Now we learned that many limitations, and beyond that, IBN controller has multiple operations, not only creating, but also updating, deleting, and topology changes. And we need to think about black box approach to support pro-priority products like Cisco. Let's run AFL again. AFL generates random inputs which are not topology aware. It cannot generate topology changes. It doesn't discover any semantic bug, and it is based on code coverage guidance, which is gray box approach. So to tackle these limitations, we propose Intender here. Intender has multiple technologies, including topology-aware intent generator, multiple operation support while considering dependency, and detection methodologies to discover syntactic and semantic bugs with a representative packet to detect the behavior of the intents, and new guidance called intent state transition guidance, which doesn't require any program code and just to receive information from REST API, so it is based on black box approach. And our design goal is implementation agnostic, so by replacing APIs, we can support many IBN implementations. Due to the time constraints, in this talk, I will look into ISTG here. ISTG works as follows. First, Intender gets the seed from the corpus and mutates based on our generation policy. Then executes each action in the scenario, for example, installing a new intent, then gets the final intent state, such as installed. Then Intender records this action and intent state into the history while running all scenario. If there is a new transition in the history, Intender stores this scenario into the corpus and keep fuzzing while finding a new bug. For the evaluation, we set up Google Cloud Virtual Machine to test Intender, and to run Intender, and we tested ONOS v2.5.1. In total, we found 12 new bugs and 11 security critical vulnerabilities, and among them, 9 bugs are semantic bugs. And these bugs can have security impacts such as network-wide denial of service and network-wide tampering. Also, we compare Intender to 4 existing fuzzers, not only AFL, but also Jazzer, which is leaf fuzzer, code coverage guided fuzzer, Jest for grammar-based fuzzer, Pass for SDN fuzzer, which mutates packets. Intender can get up to 2.2 times better in branch coverage and up to 82.6 times more number of unique errors, which generates higher probability in finding bugs. Intender also improves fuzzing performance compared to baselines. With the topology-aware input generation, intender can produce 78.7 times more valid intents compared to other existing fuzzers. Intent operation dependency can reduce 73.02% of redundant operations compared to without dependency. Lastly, intent state transition guidance leads to 1.8 times more intent state transitions than code coverage guidance. Among 11 vulnerabilities, let me introduce one of them, which cause denial of service. Due to the time constraints, I will skip the details of the logics and modules. And in this scenario, there is an intent which connects Alice in New York and Bob in Los Angeles, for example. And if requests purge on installed intent, which is not allowed in ONOS controller. So it simply rejected by ONOS controller, but due to the bug, the wrong request remains in pending. After then, if exploits link flooding attack to make link congestion, and it creates topology event like link down, then ONOS controller should recompile this intent to bypass this link congestion, and there is a backup path for the intent. Now, ONOS controller tries to look the current state of the intent, but there is a pending request. And if there is a pending request, it rejects, it ignores the topology event because the pending request will be applied later. But as I mentioned, due to the bug, this pending request remains forever. So intent does not respond to topology event anymore, which causes denial of service between two locations. To discover this bug efficiently, intender generates a single installed intent with topology awareness. It supports topology changes. It generates many intent transitions, as many as possible, and can detect connection failure. To recap, we analyzed 186 bugs in ONOS IBN and designed new fuzzing techniques for IBN. And we developed intender architecture and in total found 12 new bugs with 11 vulnerabilities. Thank you for listening to my talk. And if you have any questions, please feel free to send my email. Yeah, thank you.